Hello, everybody. You're in the right place if you're here to learn about the University of Toledo's Wright Center for Photovoltaics, Innovation and Commercialization. Welcome. We have your microphones muted and your cameras off for now to help make sure that the experience is good for everybody. And we're just going to wait a couple more minutes for a few more people to come in. And then we'll get started. And there will be an opportunity for you to ask questions. I believe you can start to do that anytime using the chat feature. And other people, if you see a question that you like, you can react to it to show that you're also interested in that. Okay, well, I think we're going to get started. It's a couple minutes past our official start time. My name is Randy Ellingson. I'm a professor here at the University of Toledo in the Department of Physics and Astronomy, and I'm one of 5 tenure track faculty members who are part of PVIC, and you'll hear a lot about our Ph.D. program, our graduate degree program, and about our Center for Photovoltaics Innovation and Commercialization. It's really great to have so many of you joining us, and this is an opportunity for us to reach out to you and provide you with some additional information while you're looking at graduate programs and thinking about where to apply. So I'm going to go ahead and just point out that this photograph here shows some cadmium telluride thin film PV modules that were installed. Some of them were installed in 2005 and others were installed in 2014. They are still operating very well and have shown minimal degradation, which is a testimony to the capabilities of thin film photovoltaics in general. These were made by First Solar.
Hey, Randy.
Yes.
There's nothing being displayed right now.
Oh, thank you very much. That's really important, and I wish I had known that to start. So let me correct that. Okay. Thank you very much. So I'm sorry that now you're seeing the introductory slide that I was referring to. That reminds me also that I want to make sure that I introduce my colleagues. So joining on this call is Mike Heben. He's also a professor of physics, and he's the director of PVIC. We have Adam Phillips. He's a research professor here and has been with the center since its inception as well, since 2008. And we have 3 graduate students. We have Nadisha Kadakambura, Aisha Patel, and actually Jared Friedel, who is no longer a graduate student. He recently completed the requirements for his PhD. So you're going to get to hear from all these people today. So I'm just going to say a few things about our PhD program before we launch into a lot of other information. I wanted to go ahead and tell you about today's agenda. So you're going to hear about the important role that solar energy and photovoltaics in particular is playing in our world. You're going to hear about PVIC. Once again, that's the Wright Center for Photovoltaics Innovation and Commercialization. And you're going to hear from graduate students and a recent graduate student on their insights into this experience and the impact that both PVIC has had on them and the impacts that they're able to have on the research and development and photovoltaics community. I'll come back and talk to you more about the PhD program and the application process. And as I mentioned earlier, you can ask questions in the chat and other people can react to those questions to show additional interest. And just very briefly, I want to just point out this is a flexible perovskite solar cell. This is a cross-sectional scanning electron micrograph image with the various materials labeled. And obviously this is a schematic of the flexible substrate. Up here we have a cadmium telluride solar cell coupon on 20 micron flexible ceramic substrate. Each of these gold colored dots is in fact a separate solar cell that we can measure. Yeah, in the lower right here are just some highlights of the opportunities that you will have if you're able to join our center. Okay, and before I turn it over to Mike Heben, I just want to say the University of Toledo, shown here, let me switch on my laser pointer, shown here in this image at right. This is the main campus. This is where our labs are located at the southeast corner of this campus. It's a beautiful place to live and to study, and the city has a lot to offer as well. We have a wonderful metro parks with places to hike and mountain bike and kayak. The largest river flowing into any of the Great Lakes is the Maumee River, and that flows right past downtown Toledo. You can see that here with the city of Toledo behind it. We have sporting events. We're well known for the Toledo Walleye hockey team and the Toledo Mud Hens baseball team, which is a farm team, feeder team for the Major League Baseball league as well. Downtown is not too far from campus, and there's a lot to do here. You can, I'm sure, learn more about it in your own research, and let us know if you have any questions. I'm going to turn it over to Mike Heben now.
Greetings, everyone. Thank you for tuning in to our webinar about our department and our program. We are focused on PV, which is photovoltaics. And the reason we are focused on this technology has to do with the fact that we feel that the world needs a lot of clean energy and power, that's CO2-free power, and photovoltaics can provide that. Photovoltaics are comprised of solid-state materials that can convert sunlight into electricity. Photovoltaics can compete with other energy sources on cost, and because of that, it's becoming one of the biggest sources of new added electricity. And it's already comprises about 5% of the world's electricity generation, and the technology is growing so quickly that it's doubling about every 2 to 3 years, which is very exciting. Next slide, please. I'm not sure if I have control, Randy. So one of the reasons we like photovoltaics is because there is a lot of solar energy hitting the planet, hitting our planet. It comes from the sun, which is a huge fusion reactor. And the process of fusion is emitting light into all directions, and about 600 terawatts of practical solar power is incident on the Earth at any given time. And all we think we need is about 15 terawatts of this power in order to provide all of the energy needs of the planet, not just the electricity needs, but also the needs for industry and heating and cooling, everything. So it's good to know that there's plenty of solar energy around, if only we can figure out how to harness it cost effectively. Next slide, please. So here's a graphic that appeared in 1999, 25 years ago. One of our colleagues at the National Renewable Energy Laboratory, he did this little assessment and said that we could get about 3 terawatts of power, which is all the U.S. needs, from the small little square that is, it's about a quarter of the area covered by all the roads and streets in the United States. And that would be the amount of area needed for a 10% efficient solar cell or solar cells, Currently, the technology is producing about 20% efficiency, so we would need only half of this area. So it's still a big challenge, but it's good to know that there's a lot of solar energy around. Next slide, please. Our photovoltaics cluster is nationally recognized. This is our National Research Council, which is a part of the National Academy of Sciences. It's recognized us for developing this cluster of educational institutions working with our local companies to help drive development and technology in the science associated with photovoltaics. Next slide, please. So our heritage, our experience in photovoltaics and our history stems back to this key person, Harold McMaster, who had a lot of inventions in his life, including machines that would temper glass and transparent conductors that we see all over in our lifetimes. For example, high efficiency windows. Here he is shown with a prototype reactor on our campus. And it's this deposition reactor that turned into the company called First Solar, which is the United States' biggest producer of solar cells. Their manufacturing facilities and most of their research labs are located very close to where we are now. Next slide, please. So who are we? Well, we do basic science, we do engineering, we do small and large scales, systems. We have all kinds of deposition and analytical equipment. Our facilities are rivaled by none. We have capabilities comparable to national labs. If you come here, you'll have access to a tremendous amount of equipment and lots of opportunities to do various kinds of research. Next slide, please. And in addition to the work that we do, we publish a ton of literature in top journals. We are well funded by a variety of different sources, and I think you'll find lots of opportunities and ways to expand your knowledge, learn new things, make contributions, and prepare yourself for the next phase in your career after you leave us. Next slide, please. Okay, I think that's all I had to say. We're going to hand it off to Adam, I believe.
You're muted, Adam.
To build on what Mike said, we are world leaders in thin film PV. And what we tend to work on, if we think about making devices, we look at two main material groups, CAD telluride, which is about 40% of the materials we make. We are one of 4 institutions in the world that have published a 19% efficient device. And we have done that with 3 different systems. The others are First Solar, which is a company that they mass produce greater than 19%, but Colorado State has reported over 20%. They have 1 system. National Renewable Energy Lab has made 19% devices. They have 1 system. We've done this with 3 systems. And when we look at 20% efficiency, we're one of 3 people. And Nadisha today just told us he made a 21% device, which is one of 2 in the world. In addition to that, we got Mike in particular is he's a PI on a grant that's kind of leading the direction of CAD telluride, and we're on a consortium that's kind of also steering this. So not only are we doing great research, but we also have the leadership here. So that's CAD telluride, that's 40% of our work. We also work on perovskites, about 40% of our work. This is a material that I guess it was discovered about, I don't know, 10 or 12 years ago at this point. And it went from a 5% efficient device to like a 25, 26% efficient in that short a time. We are leaders in that. We have made a world record tandem device in this lab. And okay, there's more than 4 groups that have made world record tandem device, but there's nobody in the world that can say they're making 20% cad telluride and have had world record perovskites. Those are single devices, small area. We're also making mini modules to try to scale up. We have leadership on this. And, 40 and 40 is 80, so 20% is other emerging materials. We have some crystalline silicon, some SIGs. Our antimony sulfoselenide is increasing, and we're exceptionally flexible that the next thing that pops up, we're going to be in that too. We don't only deposit stuff. We also have really advanced characterization, and we have one of the best groups in spectroscopic ellipsometry, which is a very specialized, non-destructive way to measure devices. And you could see this energy range from 0.04 millielectron volts to 8 electron volts is the widest range of anybody in the world. We've got groups like Randy Ellingson's group in particular that are experts in ultrafast spectroscopy and developing new equipment all the time. So we've got a lot of stuff going on, and it's not hyperbole to say that we are one of the world leaders in thin film PV. Next slide, Randy. So what does that mean for you? If you come here, is that you can get a great education and learn on cutting edge materials and become very valuable when you graduate. So let's start with our device fabrication. So you can see this diagram on the left. Basically, we can start from a piece of glass and go through our process and have a whole working solar cell. So this means depositing TCOs, which are transparent conducting oxides, because if you're going to make a solar cell, you got to get light in there and you got to get the electricity out. So it's got to be conducting and it's got to be transparent. We put down all these absorber layers and layers in between to help move the current out of the device. And then we can, you put down metal on the back. So we have many people here have started from a piece of glass. They made a whole device. Some of we're interested in actually making that substrate too. So at some point in the future, we might start from nothing and make a whole solar cell. Right. So if you're interested in device fabrication, we can do it. Mike talked about, we have very well equipped labs. We got 13 labs. Here's some numbers, 40 deposition systems total, and this 30 optical characterization, 25 electrical might be somewhere around there. But I got this picture here of an evaporator on the right as an example. So this evaporator we bought used. It was kind of a mess. There were wires everywhere. I worked with, let's see, it was 2 undergrads, a high schooler, and 1 graduate student. We stripped it clean. We got it running again. Turned this into a CAD tele device system that was giving us 17 or 18%. We had an idea about maybe we could incorporate a dopant into this. So another grad student and Professor Heben designed a little holder to get a dopant into there. There's nothing like this system in the world. It was essentially built by high school student, 2 undergrads, a grad, and 2 grad students with help from us. In addition to that, too far, Randy. In addition to doing depositions or systems, we also do modeling. If you want to do, you got to understand what we're working on. So we do some modeling, device modeling, material modeling, things like this. And so there's going to be plenty of opportunities no matter what you want to do. If you were to come here, and say you came here and wanted to work with Professor Ellingson in most universities, that would mean you would work in Professor Ellingson's lab. If you went on a tour, you would go with him. He would take his key out of his pocket, open his lab. You'd go in there. He'd come out. And when he said, okay, now you're going to go visit Mike Heben's lab, he would pull a key out of his pocket, open his lab, show you his lab. We don't have that. We have 12 or 13 labs. There are garage doors and doors on each of them. The garage doors are wide open to every lab except for two. One has hazardous gases that we can't let people in, and one is a spectroscopy lab where they want it dark most of the time, right? So we have shared labs. Almost any piece of equipment that you would want to use in these labs, you'll be able to get access to. That's not what's going to happen at other universities. And along with all this kind of sharing of equipment is that we share a lot of samples and data. So this morning, Nadisha was making some samples. He's in Professor Ellingson's group. He's going to hand them to a student in Professor Heben's group to do measurements, right? This happens all the time. Professor Jan's group makes samples. They give them to Professor Ellingson's group, Professor Heben's group, Professor Pedraza's group. There's tons of collaboration. There's very little barriers. So that's internal. Externally, we're working, we are the experts, and we're working with other experts in CAD-TEL and perovskite. And this includes working with companies like First Solar who make CAD-TEL devices. This companies that are trying to get into this. So there's no real established perovskite company. So we're working with some startups. We're working with glass companies. And of course, we're working with the national labs to help this out. So the takeaway that I want you to have from this is that you can have a lot of opportunities and do what you want. And when you're working here, we want you to be successful when you're working here, because that makes us successful. But after you're finished working here and you go out and get a job, we want you to be successful because, one, that looks good on us, but we don't just bring you in and say, here's just some random workers for us. We want you to do well. And with that, I want to comment on funding. So I had the wonderful opportunity of running out of funding in graduate school, and it sucks. But we have as much visibility as anyone you're going to meet now. We can see out 5 years. We have funding in place for 5 years, maybe not for everybody, but there is funding in place for 5 years. Most grants are 3 to 5 years. So that's as far as we can see now, but we have availability and money to pay people right now. It's not guaranteed, but right now. And so with that, I will let the graduate students tell you about how the kind of opportunities they had and what they've been working on.
Thanks, Adam. So, hey, everybody. As Randy said at the beginning, my name is Jared Friedel. I'm currently a postdoctoral research associate at UT and with the Wright Center for Photovoltaics, Innovation and Commercialization, or the PVIC as we've been calling it. So I think what we're going to do is just kind of introduce ourselves, go over each of our experiences and our histories prior to and at the University of Toledo, and share kind of like the highlights of each of our experiences. And then we'll try to be somewhat brief, but then hopefully questions from you, the prospective students, and even, Randy, Mike, and Adam can help us fill in the gaps. So to introduce myself, I just finished my 5th year here at the University of Toledo. So I arrived here in 2019. If you can't tell, I'm an American student. So I got my Bachelor's of Science at a university called Clemson University in South Carolina. And then So that was a Bachelor's of Science in Physics, and with absolutely no prior experience in photovoltaics, and really not much of any specific idea of what I wanted to do with photovoltaics in the field of photovoltaics. Other than that, I knew that it was an exciting and important topic of research. I came to the University of Toledo and entered the doctoral program right after getting my Bachelor's of Science. So, you might be listening to Randy, Mike, and Adam speak about all these things on a very technical level. And really, you might not understand a lot of what they're talking about. And that's okay, because a lot of the students that come here for research in the doctoral program don't really understand, or don't necessarily understand everything or really close to anything when they first show up. And so this program will really take you from with whatever experience you have, as long as it provides you a strong foundation, which my education did. And I definitely think the same goes for Nadisha and Aisha, who you'll hear from in a second, and will give you the education you need in order to be successful as a researcher in photovoltaics. So specifically for me, that had to do, that came in the form of performing characterization and modeling, which you probably heard a little bit about from Adam already. So I wasn't and haven't been as involved in the making of solar cells as I have in the measurement of their characteristics after they have been developed. So this really emphasizes this full range of measurements and science research that we do all together between the groups at the University of Toledo. So to get a little more technical, I did one-dimensional modeling of the electrical characteristics of solar cells using a software package known as SCAPS, SCAPS, that uses the semiconductor equations, the set of equations that describes the behavior of all semiconductors, and by extension solar cells, at their most basic level. And I applied that modeling to actually understanding their behavior in a lot of cases, as it was relevant to certain electrical and optical characterization techniques. So when I wasn't simulating solar cells using numerical software, I was actually performing both electrical and optical measurements in order to characterize the behavior of real solar cells, mainly in the form of what's known as capacitance spectroscopy, which is a suite of measurements which uses a solar cell or semiconductor device's response to a set of different signals in order to kind of get an idea of the behavior of charge, and even more specifically, defects in these materials that can affect their performance as solar cells. Okay, so that's kind of like the technical details of my research, and I'm happy to answer any more questions about that. But we also, I think as a group, and will each individually emphasize the non-research experiences, the valuable non-research experiences that we've all gained here. Me personally, I've been to several conferences across the country, including a conference in Puerto Rico, a conference in Philadelphia, Pennsylvania, and I've had the opportunity to present my research at those conferences, as well as collaborating with other institutions. I think Adam kind of listed the set of institutions that really performs the bulk of the thin film photovoltaic research in the United States: Colorado State University, the National Renewable Energy Laboratory, and commercially First Solar. And Toledo and its students get to collaborate with, across the broad spectrum of research with all of those institutions very often. And then I did just want to highlight one last opportunity that I was exposed to. If you see this top photo of me, that's me in New Mexico, the state of New Mexico, in the mountains known as Sandia Peak. And I was actually able to travel there because of my involvement in an organization founded and operated out of the University of Toledo by its students and professors called Glass City Community Solar, which instead of performing research on solar cells, actually works to install solar arrays and modules and operate and maintain them in order to benefit low-income communities in the Toledo area. And as that picture shows, it also gives you the opportunity to travel and spread that information and share the work that we do as a part of that organization. So I think as everybody has so far and will share, photovoltaics is just really embedded in the university and the city of Toledo, just at every level. So we're really exposed to such a large variety of photovoltaics and what it can do for people. So I'll go ahead and pass it on to Nadisha.
Yeah, thanks. Thanks, Jared. So hello, everyone. I'm Nadisha Katakumara. I'm doing my final year right now. So I'm originally from Sri Lanka, and I started in University of Toledo back in 2019 fall. Then I joined University of Toledo and served as a TA for a semester or so. Then after right away, start of 2020, I joined PVIC as a research assistant under Professor Ellingson's group. So when it comes to my background, if I say I finished off my bachelor's degree from University of Colombo, Sri Lanka. It was in engineering physics. Then straight away applied for the Ph.D. program in University of Toledo and ended up here in late 2019. So as of now, I'm y'all already have heard of the processes that we are going over here. As of now, I'm mainly my research areas are focused on device fabrication via thermal evaporation, and I'm into different form of characterizations, especially with when it comes to these solar cells. They do have different behaviors under different conditions. So mainly I'm kind of focusing on the temperature effect, how once you change the temperature of a device, what would be the variations occur in these devices, and how that could be helping us to identify the whatever the efficiency losses, so whatever the parameter changes occur inside these devices, because that could be useful in order to identify or in order to produce more good devices. And apart from that, I'm also into modeling, where you can instead of making real devices, we have softwares where you can model devices in a computer, and you can perform simulations, and you can guess or you can see the output, how by varying something, how the output would vary. So instead of making devices, by having simulations, things getting much more easier, and you can address a whole lot of parameters in order to identify your future plans. So so these are the things that I do over here. But if I give you the overall experience that I do have over here, so having some sort of a good background when it comes to your bachelor's degree, if you are like Jared mentioned, you might not, personally, I even didn't have any sort of an idea about photovoltaics when I was ending up here. I only had the idea where you have sort of piece of glass where the sunlight hits on it, and somehow the electricity is generated. So that level of knowledge was there, but once you ended up here, you'll be going through all the physics behind this process and how this actually happens. But in order to progress through this program, you might be some of the experiences that you have during your BSc or bachelor degree might be useful, like having little bit of knowledge in LabVIEW or AutoCAD or some programming language like Python, or especially like the experiences that you do have with like workshop instrumentations. These overall experiences will definitely be helping you in terms of like designing your own projects or like progress through your projects. Because over here, when you are in a project, you need to make sure you fix your system, so you design your system. So like whatever the requirement you need, you should be having the capability of identify the requirement and get it sorted out. So having that sort of background from your bachelor's might definitely be helpful through the progression of your PhD program over here. So because here you have all the facilities, so by having such experiences, you can like proceed through this program very easily. Other than that, like the opportunities, like Jared also mentioned, Radam also mentioned, like we have several research groups internally in the PVIC where you can like collaborate with each other and like do a lot of work. Other than that, you have like external parties such as universities, as well as like industries like for solar, where you will be helping out to figure out their projects, so you can do collaborations with them. So all of these will help you to get to know people, get to know more knowledge. You'll be having more chances of accessing more connections. And also about the conferences that Jared has mentioned, we have like for the photovoltaics community, we have like plenty of conferences happening all over the America. So as an example, if I mention, like we have a cattle workshop where all the like people who are into the cattle solar cells will get together and discuss what is going on and what are the like new updates and what are the issues need to be addressed. So recently we had this cattle workshop in University of Toledo. So this is one of the conferences that we mainly focusing on. And other than that, we have IEEE PVSC conference where like on not only cattle, but all the like solar cell community will get together and discuss about the industry and the researches going on. So this one, like last time we had this in Seattle. Before that, we had this in Puerto Rico, and the next year we'll be having this conference in Canada. So some of you all might get the chance of ending up there as well. And another conference, if I mention like space power workshop, this is a specific workshop where like all the people who are working on solar cells, which is to be sent out of the Earth, or simply the solar cells which can be used for the space applications. So a lot of people who are like working in that industry and research field will get together and discuss about how things happening and what other issues need to be discussed. So this happened in California. Likewise, like there are like lot of conferences happening, as well as like workshops. Like we have a workshop called Hope Workshop, where for a week you will be going to the National Renewable Energy Lab, and there you get the chance of like getting to know graduate students from other universities, and as a team you'll be getting the chance to work on different aspects of this solar cell production. Sometimes you might have the experiences over here when it comes to cattle, but over there you'll be getting the experiences of like production of other types of solar cells, the testing mechanisms, and what sort of like testings they'll be carrying out, and you'll be getting the hands-on experiences to try out these things in real time. And other than conferences, of course, you get one of the like main things you'll be getting is you get the like chance to visit all the plant visits, where like you will be getting the chance to visit for solar itself, and you can identify how big they are like production lines, and how they'll be like performing these things, how these solar cells are produced per hour, how many solar cells are produced, kind of thing, like how much advanced the technology that they'll be using in the world as of now. and you'll be getting the chance to visit all the glass manufacturing plants, and you get a lot of opportunities in order to identify these things in real time. So I believe this is a place where you can having the chance of getting to know the physics behind these solar cells, as well as, okay, the light goes on, as well as a place to meet a lot of people and make a lot of connections for your betterment of your future, I think. So, Aisha?
Thanks, Nadisha. Hi, everyone. I'm Aisha Patel. I'm a fifth-year Ph.D. student here at UT. I, too, am an international student. I've done my bachelor's degree in chemical engineering from India. I've done my MS in chemical engineering from Arizona State University. That's where I briefly got introduced to photovoltaics through my master's thesis work in the first place. But that work was mainly on the first generation silicon-based solar cells. Having worked on that, that kind of got me curious about thin film research. And that's how I kind of ended up at the University of Toledo doing PhD in physics with concentration in material science. With honestly, in my opinion, the coursework here at UT is so well structured that someone like me who's transitioning from engineering background to science, chemi to physics, was never really a problem. So great faculty, pretty well structured curriculum. A bit about my research. It mainly revolves around cadmium telluride thin film solar cells, mainly the fabrication and characterization aspects of it. But my thesis work is kind of twofold. So to put it in layman terms, no material is perfect, but these material defects that may not be bothersome, let's say in films that are as thick as paper, may suddenly become prominent and important to be focused on in something thinner than like a single coat of paint on a wall, let's say. So one part of my research kind of focuses on passivating or improving these faulty surfaces and interfaces to improve the overall efficiencies of the solar cells. And this other part of my work is to fabricate solar cells for space applications that are super lightweight and radiation hard. So that involves, so basically we use very thin glasses, let's say 100 microns. You saw a picture that Mike showed earlier on a 20 micron thin substrate. Use thin glasses and build a full working solar cell and work on the challenges that come with it. And I think the other grad students kind of covered this part of it too, but talking a bit about the Wright Center or PVIC, where we all conduct our research. PVIC truly has many resources for thin film. Adam mentioned all of them earlier. The work culture is quite inclusive and collaborative, mainly because there are like 4 to 5 groups, professors and their students and researchers, everyone working under the same building. And that makes equipment you need for your research easily accessible. People you need for your research easily accessible. Go up and talk to them and you can easily seek help. That has kind of helped me immensely in kind of going from not knowing much about PV 4 to 5 years ago to being able to confidently further my research based on the knowledge I've gained in the past few years. That and the mentorship from our advisors also kind of helped me in landing an internship opportunity at the National Renewable Energy Laboratory to conduct and finish up my research. Let's say, I mean, I think Nadisha already covered most of the conferences that we've attended, but we also get to attend and present our work, be it talks or posters at several national and international conferences. So overall, it's been quite a wholesome experience so far. Feel free to ask questions.
Thank you very much, Aisha. Okay, well, I'm going to step back in now and talk about a little bit more about the details of the PhD program itself. And by the way, hearing from Jared and Nadisha and Aisha, it's easy to be very proud of all that they've accomplished here, and two of them aren't done yet, and they're going strong. So you could join this kind of culture and this kind of opportunity. It's really, really remarkable. Okay, so PhD requirements for the PhD degree. 90 hours of graduate credit are required to complete your degree requirements. Those include required courses: classical mechanics, classical electrodynamics 1, that's electricity and magnetism; quantum mechanics 1, statistical mechanics; and a relatively simple physics and astronomy, but very important, professional development seminar. 18 additional credit hours, courses numbered higher than 6,100 as approved by your committee, and then 30 to 60 hours of PhD thesis research. Additional degree requirements. So the qualifier examination, if you are admitted to this program and arrive here in the fall of 2025, you will have the option, and you would be encouraged to attempt to pass the qualifier examination in the fall. This is a so-called 0th attempt. It does not count as one of the 2 attempts that you are allowed maximum to pass that exam. And then you are required to take it if you have not passed either so this is a 3-hour written exam covering classical mechanics, E&M, and quantum mechanics, and it's also a 60-minute oral exam answering relatively straightforward questions on fundamental physics, and you have to pass both parts. You don't have to pass both parts in the same attempt or the same semester, but you're required to pass it by your second official attempt, which would be during your second year here. Passing both parts qualifies you to continue on the PhD pathway. The next step along the way is really, it is intended as a reflection and review of what you have learned and accomplished in your research, and an opportunity for you to present the planned research that you have proposed to finish your thesis research prior to writing up your results. So that's the comprehensive examination, typically within 18 months of completing the qualifier exam. Finally, the thesis defense consists of a public presentation of your thesis work, followed by a closed to the public examination with your committee, in which additional deeper questions are asked to learn more about your knowledge and evaluate whether or not you have completed the requirements for the PhD. So some key points about the application process. I wanted to mention this QR code. That will bring you to information for prospective graduate students, and at the bottom of that page are all of the requirements for the application to qualify to apply, and there's also a link for the application itself. The deadline for our application is January 6th, 2025. We strongly encourage you to hit that deadline in advance as much as possible. Applications will be fully considered if they're in by January 6th. We do consider applications that arrive after that date or are completed after that date, in as much as we have available space in our program. The PhD program, if you're admitted to this program, you will receive an offer that includes a tuition waiver and a paid assistantship. Applying to our Master of Science program does not assure either of these things. In fact, it typically does not include a tuition waiver or a paid assistantship. Incoming students are directed to a teaching assistantship by default, but it's possible, depending on the availability of students for our teaching positions, that a new student could receive a research appointment. Typically, that's not decided until you arrive here, but normally you will start your research either after 1 semester or 2 semesters as a teaching assistant. So we like to get our new Ph.D. students involved in research as soon as possible. In fact, even during your teaching assistantship, if you are the kind of student who can complete your course studies and homework, and in addition to your teaching assistantship, you have additional time, we are happy to have you involved in our research for those, 5, 6, 10 hours a week, whatever you can fit in. Pairing with the research advisor does not normally happen in advance of the student, the admitted student arriving on campus. It typically happens after the student has had the opportunity to meet with the faculty in their areas of interest, and by mutual agreement, essentially, and interest, students are paired with research advisors. Adam mentioned that we have an excellent funding base here, and so students have not had to worry about the availability of funding in any photovoltaics group forever, basically, for the last 20 years. Assistantship stipend is currently $28,000 annually, with an additional $3,000 offered in the first year. This can be used, for example, for teaching assistants to pay for medical insurance, which is something that's offered by the university and is required. That $3,000 additional is paid $1,500 soon after you arrive, and $1,500 near the start of the spring semester, which is January of 2026 for people admitted to start next fall. Okay. I will be able to answer questions in the chat, or I think we can take live questions at the end as well. Our admissions process is growing more competitive. We've had about 50 applicants last year, with the good chance that we're going to have more applicants this year. We expect to admit something like 10 new PhD students to start in the fall of 2025. That number may go up or down slightly, depending on our number of available positions in our groups, but it's typically about 10. Once your application is completed, the applications move on to a review process and are reviewed together with all of the applications by our department's admissions committee. Evaluations will begin in early to mid-January, with the first offers typically sent by early February. If you are able to receive an admission offer, that will come with an April 15 response date, so that you can evaluate any other offers that you have and make a decision. Additional offers will be sent later than the April 15 response date, depending on whether or not students accept our admission offers. So additional offers can be made even into the month of May. We want to get those out as soon as we can. I just want to point out a couple things here. One is this QR code will direct you to the Google Scholar link to PVIC affiliated publications. And I want to point out here that the U.S. Energy Secretary visited our labs a couple summers ago. Here she's seen talking with 4 undergraduate students who are part of our summer research program. This is Rosa Zartman. She was a graduate student here many years ago. She works for IBM now. I'll go back for a second. Okay. Moving ahead. You have questions, we're happy to talk with you about them right now. We did advertise that webinar attendees, the first 25 registered attendees who are also in attendance today, are eligible to receive this waiver, with the caveat and requirement that you are a qualified applicant and you complete your application by a timeline that we will specify in email. We will send an email to you by early next week. We don't have any additional webinars scheduled right now, though additional webinars are a possibility. Here's a photograph of one of our graduate students with another recently finished undergraduate presenting their research at the Space Power Research and Technology Conference that's held in Cleveland at NASA Glenn. Here's another picture of Harold McMaster with the exceptional, with a prototype thin film solar cell that he and his team produced. And here are a couple images that have to do with the space photovoltaics environment and modeling the impacts of protons on solar cells. Okay, and with that, I would like to ask Krutika to go ahead and allow people to unmute their microphones so that they can take turns asking questions directly. And there are a couple other things I want to mention that have to do with questions in the chat. In general, unofficial transcripts from international applicants are accepted, and you will be required to provide an official transcript in order to be admitted to the program. So that would happen after you receive an offer of admission. For IELTS or TOEFL scores, those must be official scores provided to the University of Toledo. We also accept Duolingo and another one that's pretty obscure, I believe, called Pearson. Let me see if there are any other questions here. Okay, so yes, you're allowed to retake these English as a second language, English as a foreign language exams, and that's correct. The decision is up to you. Okay, you have access to your microphones if you'd like to, and you may be able to turn on your camera as well, and please feel free to ask questions. Don't be shy. This is your chance to meet us.
I see a question about the GRE exam. I think an earlier person asked the same question, and the answer is that the GRE, general and special GRE exams are not required.
That's correct. General exam is not required, neither is the subject exam.
We have a hand up from JPSIR. Go ahead.
Hello.
Hello.
Hello, my mic is on. Is it audible there?
Yes, we can hear you. Please go ahead with your question.
Hello. Sorry, I could not listen. Wait.
I'll type in the chat.
Yeah, I think I can hear now. Sorry for the disturbance. I want to ask. My name is Jayaprakash Misra. I am originally from Nepal, and I have completed my master's a few years ago. I have been working on a thin film with my professor, and I'm also helping some other thesis students with that thin film on a gas sensor. So I want to ask that how much helpful it will be when I apply for thin film PV. That's my question. Thank you.
Yeah, thanks for your question. And I think that's really helpful to point out that I mentioned that our program has become more competitive. Some of our applicants have had the opportunity to do real photovoltaics research and become part of, in some cases, high-profile publications. Certainly not all of our successful applicants fit into that category. Any hands-on experience that you have and any research experience that allows you to develop insights into how material science works is of great value to you and to us. And so your goal in your application is to demonstrate what you have learned so that we can see that you have done something that's meaningful to you and will be meaningful to us. And so that kind of experience is really important. I think the strongest applicants have some hands-on experience. They can demonstrate that they have learned, from their research, and they also can convey strong communication skills. Writing is very important. The ability to speak and engage in scientific conversations is very important as well.
Thank you,
We have
sir.
another hand. Yes, you're welcome. We have another hand up.
Quickly, Randy, lack
Yes.
of research experience does not disqualify you.
That's right. Mohammed Usman Nawaz.
Hi, my name is Usman and I'm from Pakistan. Actually, my question is that I don't have a background in physics. I'm from engineering background, but I do have experience in perovskite solar cell and device fabrication. I have submitted my application, so I was just wondering, does this impact on my application as I'm not from physics background?
No. However, as I mentioned in the chat, I believe one needs to demonstrate convince the application committee that you have the aptitude to learn and pass the physics requirements, right? So the qualifier exam tests your knowledge of physics at let's say a high undergraduate level. And so, if you believe you're going to gain admission, then I would say start studying. Start studying physics, the fundamentals, and persuade the committee that you are a good applicant. One of my earliest students was an electrical engineering major and did phenomenal work in photoluminescence and time-resolved photoluminescence and analysis, and went on to be very successful.
Okay, thank you.
Yes, you're welcome. We have another question from, is it Sadeh?
Hi, Professor. I appreciate your consideration and your time. I have a question like the previous one. I have a background in material science, and I focus on electrochemistry, surface science, and other kinds of things. Providing that I pass the exam, after I get the admission, I can, get the admission. I want to ask you how to, choose the students, and how you, assess their abilities during your process. Thank you very much.
Was your question about how professors choose or agree to have students join their research group, or were you asking about the application process for the program itself?
No, I wanted to ask about how professors choose the students, and even about your application, because as I mentioned before, I don't have any background in physics and the photovoltaic, and this kind of subjects. I have background in material science and surface engineering and other kinds of things. I have any chance or not? Yeah.
Well, I'll just repeat what Adam Phillips said, and that is that lack of experience does not disqualify you. It is frequently, but not always. It depends on the type of research experience and the rest of the qualifications of the applicant, but it can be very helpful. In your case, if you have experience in other fields that are somewhat related, then one of your important goals will be to demonstrate your aptitude and competence and knowledge in that field, and your, I guess, understanding, right, of the field of photovoltaics. If you're applying to our program because you want to work on photovoltaics, then you need to do some work on your own to teach yourself at least the basics. And the basics are not talking about the basics of detailed semiconductor physics, but to understand the problem and to understand as much as you can about it will help you in your application process.
Thank you very much.
You're welcome. Thanks for the question. Any other questions? Are there any other questions in the chat that I missed? Let's see here. Okay. Looks like questions in the chat have been answered. So we're 5 minutes
Hello.
over time. Hello. Sorry, go ahead.
Hello. I'm Sumaya. And actually, one question is in my mind. According to the PhD. Hello.
Hello. I can hear.
Are
We
you
can hear you. Yes.
Okay. Actually, sir, I have completed my PhD in physics in material science, and I have means so much experience in the quantum mechanics and classical mechanics and condensed matter physics, etc. So basically, my work in the means material science with the specialization in nanomaterials and the nano devices and their fabrications. And really, I'm interested in the working in the solar cell fabrication and measurement applied to the various postdocs. If my application didn't go through and I'm interested in doing PhD again, so what's the requirement for that?
So let's see. If I understand correctly, you've applied for postdoctoral research positions because you have a PhD already in material science?
Yes, I already did, but means a PhD in material science.
Yes. So I don't really know what to say other than I think that if you have a PhD in material science, that you are probably better off looking for a postdoc than starting over in a 4 or 5 year program.
Okay.
Yeah, and you can reach out to me separately by email, but I think that that's the answer. And if you've applied here, I can tell you that we continue to review applications. So if you have not heard from us, then you will eventually.
Okay. Thank you.
Okay. Any other comments from my University of Toledo colleagues before we wrap this up?
You got one more hand up, Randy.
Oh, okay, great. Okay, Navneet, please go ahead.
Greetings of the day, Professor. Like my question, maybe you like maybe not understand you well. Like my question is, I got 7 band overall. That is up by university criteria, but your TA assistantship you need 6.5. That in that I'm lacking. So should I retake this exam or like this is what should I do?
Yes, if you want to, you need to have you need to be eligible to serve as a teaching assistant, and so we have a certain speaking requirement there, as you know. So, if you did not meet that requirement, then yes, you should retake that exam.
Thank you, Professor.
Yep, you're welcome. Okay, any other questions? Thank you all very much for joining, and thank you for taking time to ask questions. As I mentioned, well, I am the chair of our graduate admissions committee, so if you have questions that are not answered through the prospective students information or through, if you've emailed me already, the email that I provided, then please feel free to reach out to me and I will do my best to get an answer to you. We will begin our evaluation of applications in January, and we hope to have our first offers out around the end of January or early February. If you do not hear from us, that only means that we have not reached a decision on your application. We typically do not decline applications until we have sent out all of our acceptances, and as I mentioned, that sometimes does not happen until sometime after the April 15th response deadline. Okay, on behalf of my colleagues, thank you again for joining us. And have a good rest of your day or rest of your night.
Thank you.
Thank you.